Hello, in today's video we will be basically just talking about the fundamental concepts of a sound wave. So after watching this video you should be able to describe how a sound wave moves, be able to talk about the wavelength of a sound wave and some other principles and properties of sound waves. So let's get right to it. So first, what is a sound wave? Well, basically a sound wave is created by an object that is vibrating, and those vibrations cause a propagation, which basically is a movement through a medium from one location to another. Okay? And so the medium could be air, so like right now you're hearing my voice, basically my vocal cords are vibrating and it's causing air to compress and expand and basically causes you to hear sound. Okay, and that air would be a medium, or water could be a medium in which sound travels through. Remember, sound transports energy and not matter. Okay, so in the previous unit we talked about taking a wave and creating a wave on a rope, and it's not like you get a big pile of rope at the end of the wave. Same with sound. Sound is transporting energy, not matter. So if you take a tuning fork and you strike it with a hammer or a mallet, basically it produces a sound wave, okay? Because the tuning fork starts to vibrate and you get a sound wave. So what kind of wave is sound? Okay, we've talked about two types briefly. We've talked about mechanical waves and electromagnetic waves. A sound wave is a mechanical wave, and the reason why is because it requires a medium through which to transport. Okay, if I took all the air out of this room right now, you'd see my mouth moving, but you'd hear nothing. It'd be kind of like would be like in outer space. Okay, you need a medium for sound to transport through. Whereas an electromagnetic wave, such as like light or X-rays or radio waves or microwaves, those do not need a medium to transport through, and we're going to talk a lot about those later on. So sound waves do need a medium, or mechanical waves I should say, do need a medium. Electromagnetic do not. So here's just an example problem. Which type of wave listed below requires a medium through which to travel? Sound, television, radio, or X-ray? Well, basically television, radio, and X-ray are all electromagnetic waves, okay? And those do not need a medium to travel through. Sound, though, does, and so that would be our answer, sound. How does a sound wave travel? So what does a sound wave look like? Sound is a longitudinal wave, so basically it expands and contracts, kind of like if you take a slinky, and down here you can kind of see if you take your hand and you push on the slinky, you cause these compressions, and this is called a refraction, which we'll talk about later on. And basically what a longitudinal wave is that the motion of the medium is in the direction that is parallel to the direction of energy transport. Okay, so it's all going in the same direction, and again, just kind of think of this slinky, and you're pushing your hand, making it compress, and that's how a sound wave travels. Actually, the air gets compressed and it expands. So there's these things called compressions and refractions, which is how a sound wave travels. And a compression is basically an area of high air pressure. Okay, and these little black dots here are supposed to represent like air molecules, and you can see that that's an area of high content of air molecules or high air pressure. Same with this point, same with this point, and same with this point. Then a rarefaction is a region of low air pressure or low air molecule density, and those are like this point or this point or this point. Okay. So how do you measure a wavelength? Because sound waves don't have like crests and troughs like we've been talking about previously. So what is a wavelength? Well, a wavelength is the distance from one compression to the next, or one refraction to the next. Okay, so from this point right here to this point right here, that distance right there, that would be a wavelength, or also known as lambda. Okay, that would be a wavelength. Or on the flip side, I could do a refraction from one refraction to another. That would be a wavelength also. It doesn't really matter what you choose. Either way, that's how a wavelength is. And this picture is supposed to kind of show you the same idea. Now, again, sound waves don't travel like this, that they go up and down, but this is just to kind of show you, comparing waves that we've talked about in the previous unit to now this one, how it kind of travels. So pressure increases as time goes on. So you see an area of high pressure is a compression, and area of low pressure is a refraction. So here's an example problem for you. A longitudinal wave moves to the right through a uniform medium as shown below. And I apologize, this picture is so poor. Let me see if I can get a different pen color here so you might actually be able to see a little better what I'm doing here. We'll go with magenta. All right, so there's a point right here, and it's labeled A. There's a point right here, and it's labeled B. Point right here, and it's labeled C. Point here, and it's labeled D. And then point here, and it's labeled E, which doesn't look so good. So it says points A, B, C, D, and E represent positions of particles of the medium, so it could be air, water, whatever. What is the direction of motion of the particles at point C? So at this point right here, what is the direction of motion of particles at point C as the wave moves to the right? Well, the very definition of a longitudinal wave is that the particles move parallel to the wave direction. So particle C is going to be moving left and right. And that would actually be our answer, left and right. It will not move up and down because that would be actually the definition of a transverse wave. But a longitudinal wave compresses and then expands. Question 2, between which 2 points on the wave could you measure a complete wavelength? Okay, so you need to find 2 points on this wave that are in the same position, if you will. And if you look at A here, and B, that's no good, right? A is kind of part of a compression here. B looks like it's kind of in the middle of a refraction. But if you look at A and C, they look like they're in the same exact spots, and especially in terms of their point in the compressions, right? So it looks like A and C would equal one wavelength. Okay, one wavelength would be A and C. Okay. That takes care of this video. I will see you guys next time.